All right, let's go ahead and get started, shall we? Folks ready to learn everything you need to know about computer science in 45 minutes? Well, if that's what you're hoping for, I'm sorry, I'm not going to be able to deliver. But hopefully I'll be able to give you a taste of what's going to happen. So my name, first of all, before I begin, can everybody see my slides? Can I get a couple thumbs up or something? Just let me know if you could see them. Excellent. So welcome. This is going to be a sample lecture for the Master's Program in Computer Science at the University of Chicago, as well as the CAPP program, which is our joint program with Public Policy. My name is Chelsea Troy. I am a lecturer in the Master's Program in Computer Science. So far, I've taught iOS development, Python programming, and mobile software development. So we'll see where I end up next. But tonight, I've ended up here with you to talk a little bit about the program and specifically to give you an idea of what it would be like to be a student in the program. So that's me. My name is Chelsea Troy. I am a lecturer in the program. Let me get my focus back on the thing here so I could change the slide. Excellent. So before I begin, we'll talk a little bit about the program. So this program, and specifically I'm talking about the MPCS side of the house here, it's designed to prepare you for careers in the tech industry. That's what I have. I'm a staff software engineer at Mozilla. I have a career in the tech industry, as do a lot of the instructors here at the MPCS. So we're going to prepare you for careers in that industry with us. Now, here's the thing about the tech industry. Tech is a high leverage industry where you're going to have the opportunity to impact millions, maybe billions of lives. So we want to prepare you for that. While you're here, you'll learn how computers work. You'll learn about the kind of mathematics that we most often use in programming, and you'll learn why the humble search engine requires algorithmic masterpieces to work properly. You'll learn about the systems that undergird your operating system and the internet. You'll also have the opportunity to practice applied skills, things like testing, software architecture design, and writing mobile apps. You'll write code in multiple programming languages, and you'll take at least some of the partial course selection listed on this slide. But you haven't done any of that yet. In fact, maybe you're deciding right now whether you want to do it at all. So for this lecture, I'm going to take a step back. And instead of assuming any of this knowledge, we're going to talk about this. What could go wrong in an application? And how can we tell if it's wrong? And how do we know how bad it is? And what can we do to fix it? Does anyone know what this is? Type in the chat if you do. I suspect we might get somebody. It might be obscure. So this is the Mars Climate Orbiter. This thing launched out of Cape Canaveral in December of 1998. It was headed for Mars. The idea was that we were going to use it to learn about the climate on Mars. In September of 1999, as it approached the red planet, though, it went around behind the other side of the red planet and we stopped getting data from it. We never got data from it again. We lost this spacecraft trying to put it into orbit around Mars. What happened? Does anybody know what happened? So here's what happened. So back on Earth, let's back up to back on Earth. The craft itself was designed and operated by Lockheed Martin out of Denver, I believe, a contractor here in the United States, who used English units for their calculations on the spacecraft. Meanwhile, the navigation system was designed by the NASA JPL, the Jet Propulsion Laboratory down in California. And that navigation system was designed with metric units in mind. So we got a spacecraft that's receiving commands in English units and a navigation system that uses metric units. And as a result, unfortunately, we flew it way too close to Mars's surface and the atmospheric pressures likely broke it up pretty quick. Now, here's the thing. The folks who designed and built this spacecraft were literal rocket scientists. So the question is, how could something like this happen? This is what I want you to understand about tech in general, is that this right here demonstrates the curse of leverage. Tech is a high leverage field. And by placing yourselves in a position to decide how software works, you place yourself in a position to succeed at or fail at putting a $125 million orbiter into orbit around Mars. You put yourself in a position of responsibility, possibly over safety and lives. Now, that's not so fun to talk about, and I want to avoid triggering examples in our mid-pandemic sample lecture. So we're going to adopt a more lighthearted example for this lecture in particular. Are y'all able to see the picture on this slide? You're not able to see the picture on this slide. Well, that is unfortunate. It is a parrot. It is a beautiful parrot, and so I'm sad that this picture is not showing up for some reason. Maybe it'll show up eventually. Sometimes we have a little bit of an issue with Zoom and the presentation. But the picture is of a scarlet macaw. Are folks familiar with a scarlet macaw? In fact, let's do this. Let's do this. Y'all can see this, right? All right, excellent. So these are scarlet macaws. We have one of these here in Chicago, cared for at the Shed Aquarium. So if you come to school here, you're likely to meet her. Her name is Serrano. She has a roommate named Pablo, who I believe is a blue and gold macaw, also a species of greater macaw. Take a look at this. This is, I believe, what Pablo looks like. Pablo and Serrano are friends here at the Shed Aquarium. Now, if something were to happen to Pablo or Serrano, they'd need help from a vet. And for the purposes of this class, we're going to imagine that they'd be brought to a special veterinary clinic just for birds. Now, just like a human hospital, the parrot emergency room has triage and bird beds, etc. Everything that you're familiar with from a human emergency room, we can imagine that this emergency room has is just for birds. Now, let's also imagine for a moment that you are all on the engineering team that will be building the software used at this parrot emergency room. So let me show you what this might look like. Eventually, in the course of this lecture, we're going to walk through together a risk analysis for this diagram. But first, I want to show you what we are talking about. The way that I'm going to do that is I am going to share I'm going to share in the chat a link as soon as I figure out how to do that. Here we go, more, chat. So there's now a link in the chat. You don't have to go there yet, but eventually we will be using that link. Let me show you what you are going to find at that link. So if I come up here to my second tab, you can see what I've got at that link. Now, I'm not going to put this in presentation mode, but I do want to make sure folks can see this. You can see my screen so far. Excellent. So what you are looking at is what we in software engineering refer to as a class model diagram. A class model diagram. Now, we won't talk today specifically about why it is called a class model diagram, but I want you to think of this as a flow chart for the way that data might flow through our software system. So let me do this. Let me go to View, Zoom, and zoom it in a little bit. Now you can't see the whole thing anymore, but that's okay, because what I'm going to do is I'm going to walk you through this system from start to finish. This is the system that we are using to help automate notifications for veterinarians in a parrot emergency room. Now, there are three inputs of data that are really important for our system. The first one right here is a breed information API. API stands for Application Programming Interface. You don't have to worry about that right now. What I want you to do is think about this as a resource for information about different breeds of bird and what their vital signs should be. For example, maybe a macaw is supposed to have a certain weight, a certain heart rate, a certain breathing rate, a certain temperature, etc., etc. whereas one of the smaller birds, let's say a rose-breasted cockatoo, is supposed to have a little bit of different vital signs and, of course, a different weight. This breed information API is going to help us understand what is normal for a specific type of bird. Okay, that's the first source of information that we're using in this system. The second source of information that we're using in this system is some stuff that the veterinarian enters about the bird. So the vet has an iPad, and when the bird gets registered in the system, the vet is going to go through, maybe ask the owner some questions, maybe make some observations on the bird themselves, and they're going to enter information about this specific patient's history. So that's this iPad right here, okay? So that's the second source of information. First, what's normal for this breed? Second, what do we know about this bird at intake based on what a veterinarian has observed? Third, we have a patient monitoring harness, okay? This right here is, I believe, a caïque, and he is wearing a harness. So what this harness is going to do is the bird gets taken into the system. We put this harness on him, and what it does is it monitors their vital signs in real time. So we always know what the heart rate, what the breathing rate, what the temperature, etc. is on each of the birds in our system. That's the third source of information. So we've got the first source of information, what's normal for this breed. The second source of information, what has the veterinarian observed? And the third source of information, what are the bird's vital signs right now? Okay? Now, the breed information and the patient monitoring harness both depend on the internet to function. What they're doing is they're sending the data to what we call a remote server, and then we're going to be fetching that data later to do something with it. The iPad information doesn't work that way. Instead, we have a shared database, okay? A shared database between all of our applications. Maybe we host that on site. You don't have to worry too much about these technical details. They're there for those of you that are interested, but those are our three sources of information, okay? All right, so now we have all this info, breed information, patient history, heart rate, breathing rate, temperature, etc. And they come to this point in the application. And that point in the application is called the condition risk evaluator, okay? The condition risk evaluator, and what that thing does is it identifies, it takes in these three pieces of information and it identifies a risk level for that bird. This bird is doing okay. Maybe this bird needs to be seen sometime within the next day. Maybe this bird needs to be seen sometime within the next hour. And that bird, which is in critical condition, it needs to be seen immediately. A vet needs to be over there right away. Okay? Once we have all of this condition risk evaluation happening, we go over to the prioritizer. So what the prioritizer is it's essentially a sorting function that sorts the birds from top to bottom according to who needs to be seen first. So maybe a bird that needs to be seen within the next hour is ahead of a bird that needs to be seen within the next day, for example. And vets can then go down the list and make sure that they have seen all of the birds in the appropriate order so that everybody gets what they need. Now, there's also a threshold for critical condition. And if a bird exceeds that threshold for critical condition, now the vet's phone is going to receive a notification that a bird needs help immediately. Once again, we have a situation right here where we've got some code evaluating risk, right? We've got some code sorting the birds, and then we have this notification system that relies on either the internet or maybe a cell network or something like that, okay? Now when we zoom out a little, view, zoom, fit, and we look at this entire system, what we see are three sources of data that all feed into this one spot where we have to do some logic. And then we need to prioritize, sort based on that logic. And then if any of the birds are in critical condition, we need to send a notification. That's our software system. We don't have to get too far into the technical details for you to start to notice some things about this system. We're going to talk about that in just a second. I do want to say that you can go ahead and ignore this stuff in the upper right-hand corner for now. Okay? But for this first exercise, what we're going to be doing is we are going to be going through the first part of a risk evaluation for this system. Now, at this point, we are all together going to work on answering the question, what could go wrong in this application? What could go wrong in this application? Now, normally in my classes, the way that we do this exercise is that we break into groups of 3 or 4, and each group of 3 or 4 gets their own version of this diagram. And they all go through it for about 10 minutes. And then after they have gone through all of that stuff for about 10 minutes, we regroup and we go through what everybody said, and we evaluate. Unfortunately, we don't have time in this lecture to do this the way that we would normally do it in one of our classes. So I have adjusted the activity for today. I've adjusted the activity for today, and I'll be honest with you, I'm not 100% sure it's going to work, but we are going to try. Now, here's what's going to happen. All of you should have edit access to this document. All of you should have edit access to this document. And what you are going to do is you are going to go through and you're going to put onto this document, type in wherever you think something could go wrong, what you think could go wrong. So let me show you an example of how this might work. I'm going to go to View, Zoom, and I'm going to zoom all the way into 200% for now. Now I can't see the whole thing at once, but that's all right. I'm going to come up to this sample text box for copying and pasting, and I'm going to hit Command C. All right? And now maybe I want to go over here, and I want to identify that if the internet is out, then this situation is not going to work. So I'm going to paste my my text box. Let me grab this. All right. I'm going to paste it right here, and I'm going to say internet might go out. And I'm going to make it a little bit smaller because 18-point font's going to be too big for us all to work together on. Let's say I'll make it an 8. Now, it's okay if you put the same thing as somebody else. These don't have to be unique. That's fine. It's all right if you go through independently and identify on this diagram stuff that you think could go wrong. Another change I'm going to make before we get started is I'm going to make this sample text box a little smaller so that this is easier for everybody to participate in together. We're going to go through, we're going to take a few minutes, and I want you to copy this, paste it anywhere where you see something that could go wrong, and type in what you think could go wrong. In the process of doing this exercise, we might hit the Guinness World Record for the largest number of engineers to ever participate simultaneously in a risk evaluation. But we'll see if we get there. All right, I see some copying and pasting happening. That is excellent. I'll give you all some time to do that. Let me see if I can get you a little bit of thinking music for you to do this for a couple of minutes. Let's see here. Let me come over here and grab this. And then let me go to screen sharing. I'm going to stop sharing for just a second. And then what I'm going to do is go to advanced music or computer sound. All right, I'm going to give you a few minutes on this. All right, excellent. If you're not all the way done, that's perfectly okay because we're actually going to be coming back to this. Hold on, I see somebody in the chat has asked if they can have the link again. There's the link again. All right, so we're going to come back to this. Don't worry, but let me share my screen again here. Let me share my screen again here with you. This is like always a process. It's never not a process. Here we go. And let me share this with you. All right. So you've done a couple of initial risks. You've identified some things that you think could go wrong. That's great. You've done a little bit of thinking about it. Now we're going to start to refine your knowledge. We're going to start to add some understanding for you to what might go wrong in this application. And the way we're going to do that is I'm going to talk to you a little bit about what you might be looking for in an exercise like this. You've already identified a few things I see on the diagram here. One of the breeds is missing, the internet could go out, the cell network could go out. These are all great things to identify. Now, let's talk a little bit about some categories that are going to help you think through what you're looking for. All right? And then we're going to try the activity again, and you can think about some of these things and add some more stuff. All right, so number one on what could go wrong in an application, functionality. So this is the one that people tend to think of, and this is the one that a lot of our examples so far are in. So functionality means that something might not work or it might not work well, right? There's a button that for some reason doesn't work, or it takes you to the wrong place, or there is, let's say, like the form for the veterinarians isn't entering properly or something like that. That is functionality. But there are also lots of other things that we can look for to go wrong in an application. For example, scaling. Something could fail when a lot of people use it at once. That was one of the things that I worried about for this lecture, in fact. I didn't know what it was going to be like to have this many people editing a Google slide at once. Would it work? Would it fail? I wasn't sure. The documentation said that up to 100 people are supposed to be able to edit it at one time, but theoretically what should be allowed to happen and what happens in practice a lot of times are very different things. So that's scaling. 3, robustness. Something could fail when given invalid inputs by accident. A great example of this is forms. So for example, if you have a form and somebody puts in too long of an entry or too short of an entry, or a number where they were supposed to put text, or text where they were supposed to put a number, maybe the whole app crashes, or maybe it handles that gracefully. But if you have to put in the exact right thing in order for everything to work in an application, then it's not very robust. So those are the first 3. There are 3 more. Security. So we talked about how maybe the application breaks if somebody accidentally puts in a wrong input. What about if somebody deliberately attempts to hack our application? Is it going to fail? Is it going to protect these birds' private information? Is it going to protect their owner's private information? Is it going to protect their owner's financial information? This is all really important stuff for us to be aware of when we're building a critical system. So that's security, right? So far we've got what? We've got functionality, we got scaling, we've got robustness, we've got security. We got 2 more. Accessibility. This is a really important one, especially in mobile development or front-end development. Something could fail for users who rely on text enlargers or screen readers or captions or large tap targets or high contrast. Anytime somebody is using a screen, is interfacing with our product, it's important for us to make sure that it's accessible to everyone who would want to use it. For example, suppose that we had a veterinarian who had low vision. It's important that they also be able to use the form. Suppose that we had a veterinarian who was deaf. It's important that that vet also be able to receive notifications about a bird in critical condition. And finally, inclusion. Something could fail to consider the needs of people it's supposed to serve, but who aren't the decision makers on the app. We saw a great example of this today. Slack HQ, perhaps you're familiar with the product, released a feature that will allow Slack users to message each other across Slack communities. So Slack released this feature, but the people who were in the room when the feature was conceived of didn't think about the way that that feature could be used to attack, demean, and harass people. And so, as a result, they released this feature without the proper moderation tools attached, without the ability for people to block other people, and without the ability for people to protect their personal information from other users of the Slack product. They're getting a lot of blowback right now on social media. And the reason for that is that marginalized communities, who are often the targets of harassment, were not included in the decision-making process about how that feature would be designed. Or perhaps a few of them were included, but their concerns didn't make it into the final product. That's a big risk with an application, because the leverage of a software product is so high that it is easy to hurt people, even if you didn't mean to. So, those are our 6 things, right? Functionality, scaling, robustness, security, accessibility, inclusion. Now, what we're going to do is we're going to try the exercise that we started a minute ago again. But now you've got these 6 categories that you can think about. And my hope is that this will help you come up with maybe a few more ideas for what might go wrong in this app. This time, I'm going to give you a few more minutes. Last time I teased you with about 90 seconds of time. This time I'll give you, we'll say a solid, we'll see when the cursors slow down. How about that? We'll see when the cursors slow down. So let me go ahead and stop sharing here and set you back on the Google Doc and put on a little bit more thinking music for you, which I should now be able to do because I'm a little better set up for that. All right, here we go. Yeah, look at you go. What do we think? I see a couple cursors still moving, maybe slowing down a little bit. This is awesome. You know, I think probably one of the coolest things about teaching classes remotely is stuff like this, is being able to watch groups like collaboratively work on stuff like this at the same time. I just think it's so cool. All right, so we've identified a whole bunch of stuff that could potentially go wrong in this application, right? So let's take a look. Let's zoom in a little bit, and we won't talk about all of them, but we'll zoom in, take a quick tour, see what kind of stuff people identified. Oh, y'all are good at this. Yeah. All right, so the great thing about being a software engineer is that you basically get paid to be anxious about stuff, which works out great for me. And that's what activities like this are about. Is it's taking the things that you're nervous about and putting them together in a framework that helps us to mitigate those risks as software engineers. So I see some things on here. Poor security leads to data tampering, delayed response from the API rate limits to prevent info retrieval. Yep, if we've got too many parrots, that could be an issue. A mixed breed. This is exactly the kind of thing that gets caught by a system like this, because you do not expect somebody to walk in with, for whatever reason, you know, when we build these kinds of systems, maybe we think about purebred parrots, and we don't necessarily know what to do when somebody comes in with Catalina macaw, for example. That's a hybrid. And what maybe is supposed to be happening there, right? Great example of a situation where what we anticipate as engineers doesn't always match up with the real world. We got to put stuff in categories, but we have to remember the categories are not real. They're not real. We can use them to model the world, but ultimately we have to know what's going to happen if something comes in outside those categories. All right, let's look at the monitoring harness. Too many patients at once. Lack of accessibility for vets with disabilities. Yep, the iPad might not include options for the blind, totally. The harness might break. False readings due to environmental conditions. The harness doesn't fit properly. Faulty harness, out of battery. Doesn't work for birds of all different sizes. Sensors incorrectly calibrated. Oh man. You know, I don't think we have any bird owners in the audience. Because if there were a bird owner in the audience, one thing that would be on here is bird rips off harness. Because they are experts at Houdiniing their ways out of harnesses. Owning a bird is like having a 5-year-old living in your house for 75 years. I don't have one. I love birds, but I am certainly old enough at this point that if I were to adopt a baby bird, I would have to put it in the will. All right, now let's take a look at our condition risk evaluator. It depends on 3 services to proceed. This is a big problem, right? We might have scaling issues as it's a bottleneck, or let's say one of the services is down. What's the condition risk evaluator supposed to do? Syntax error in the code for evaluating conditions, totally. System crashes with too many users at once. Yep, this is a classic scaling issue. Faulty logic triages incorrectly, and in-need birds go uncared for. This is a big deal, because this is the kind of thing where we need to evaluate a trade-off as software engineers, because probably, like I said, we are using models. When we write software, we are building a model of the world. But we must remember that that model is not real. It's not real. And sometimes it's going to be wrong. And so we need to decide what direction we want it to be wrong in a lot of times. We have to make a decision about how sensitive it should be for how, how many false positives we're willing to tolerate, how many false negatives we're willing to tolerate. Would we rather a bird go uncared for, or would we rather the system be a little bit too sensitive and maybe release notifications on birds that aren't exactly in critical condition? That's something that we have to think about, right? And maybe under normal circumstances, we want it to be a little bit too sensitive. But then suppose there's some sort of like surge and we need to see more birds than vets have capacity for, then maybe we need it to really only tell us about the birds that really do need us right away. So how we want the system to work might depend on conditions. The threshold might not trigger the notification. Communication might not be possible. The vet has no phone, or the phone has been broken. Security issues with the prioritizer. Someone might hack it. and just push their patient up in the queue. Yeah, totally, right? Crashes when two patients need help at the same time. Mechanisms may not be in place in the case that there aren't enough specialists available to serve all the patients. Yep, this is that surge thing we were talking about, right? So you've identified a lot of risks here. A lot of stuff could go wrong in this application, right? So how are we going to address it? We're going to fix it all at once, right? That's why you're coming to the MPCS, is so you can learn how to fix it all at once. Well, unfortunately, I wish I had good news on that front, but I don't. The truth is, I would not be able to fix all of this stuff at once. Even my entire team would not be able to fix all of this stuff at once. And so it's very important for us to understand how to prioritize it. Just like our system is designed to prioritize birds, our engineering system, the way that our team works, the way our risk analysis work, needs to prioritize how to address risks. So let's talk about that now a little bit. We're going to practice analyzing some risks ourselves, but first we need to talk about how you would go about analyzing those risks. Here we go. So let's talk about gauging risk priority. Here's the thing. There are a million systems out there to help you gauge risk priority, right? You've got everything from various Sigma methods to big, long 700-page books about evaluating risks. And those are great, and the truth is that in the real world, they don't get used. They don't get used, they're too complex, it's tough to coordinate a team on so many things. So instead, we're going to talk about a little bit of a simpler system that's accurate enough to be useful, but simple enough to be used. And it involves understanding 3 risk amplifiers. Risk amplifiers are things that make a risk bad or that make a risk worse. These are the things that you want to watch out for. You want to make sure that you prioritize risks that have 1 or 2 or even all 3 of these risk amplifiers. So here's the first one, catastrophic. Is this catastrophic if it goes wrong? Good example of that for a web application would be if the web pages both just completely stop loading. That's catastrophic. The software cannot complete its core function if this is broken. That is a catastrophic risk. Second, likelihood. Is this likely to go wrong? Right? So a good example here might be, suppose that you have servers set up in several regions all over the US to make sure that in the US, our bird triage system isn't going down. It's still going to go down if every single region is down at the same time. Is that likely? No, not particularly likely that all the regions are down at once. What would be more likely would be a veterinarian accidentally enters something wrong on the form. That's a risk that's pretty likely, right? People mess up. Our systems have to take into account that people mess up, right? We see an example of a case where this didn't happen going on right now. There's an extremely large ship essentially stuck in the Suez Canal. It's blocking all traffic in and out of the Suez Canal, which is the route by which container shipping happens, like to Europe and Northern Africa. The ship is massive. It's big enough that broadside it could block that entire canal and all shipping. The system didn't take into account the possibility that that could happen by allowing a ship that could block the canal to be in the canal in the first place. We got to take into account that sometimes things go wrong and consider maybe the Suez Canal is too small to allow a ship that could potentially block the entire thing, right? We got to think about our systems in that way. So, is it catastrophic if it goes wrong? Is it likely to go wrong? We've got those 2 things. The third thing is, if this goes wrong, could it go uncaught? And for how long could it go uncaught? Now, this is, in my view, the most insidious of these 3. Because when people think about whether something could go wrong, they think about how bad it could be, and they think about how likely it is to happen. But they don't necessarily think about this third one, which is stuff where you don't realize it's wrong for a long period of time. An example of this might be if hackers get into the system and they're able to access people's personal information or financial information for an extended period of time. Or if they have the opportunity to access people's medical records for an extended period of time. If we don't catch it, we don't take access away. If we don't catch it, we don't plug the security hole that allowed those hackers to get in the first place. Another example might be if something is corrupting our data in a way that makes the data fit the format it's supposed to fit, but makes the data wrong. Maybe something is converting all of our text information about the parrot's condition at intake into wingdings, right? Into the wingdings font for some reason. And then the database doesn't take wingdings, and so it all gets converted to gobbledygook. And we lose all of our intake information about the parrots. When that kind of stuff goes uncaught, it ends up causing mega damage. So we want to be aware of that possibility and think about how to reduce it. So we got 3 risk amplifiers. Is it catastrophic if it goes wrong? Is it likely to go wrong? Could it go uncaught? Right? And now, here's the next activity that we're going to do. We are going to come back to this diagram, and here's what's going to happen. So in the upper right-hand corner here, you see 3 little text boxes. You've got catastrophic. It's this little fire icon. You've got likely to happen. It's this little dice icon. And we've got likely to go uncaught. And that's this little detective icon. So now, here's what we're going to do. We're going to copy those icons. Yep, looks like somebody already guessed what we're doing here. Nice. You copy these icons and paste them next to any risks that you think qualify for these amplifiers. Okay? You can copy and paste as many of them as you want. Okay? As many of them as you want. And you can put all 3 risk amplifiers on one risk if you want to. Maybe some of them just have 1. Maybe some of them have 2. Maybe some of them have all 3, right? So what I'll do is I'll give you a few more minutes to do this. Let me put on some thinking tunes for you. Here we go. You don't have to put it in the text box if you want. You can just put it next to the text box if that's easier. Look at all those fire ones. We got a lot of potential catastrophes going on. Fires everywhere. I see a few dice. We got some likely stuff happening. I see a couple dice next to each other. I wonder if that means that's super likely. Ooh, I see a detective. What's that detective? I can already tell some of you are going to end up software engineers. We'll do this for another 90 seconds. Excellent work. Look at this thing. Have I scared any of you off of software engineering yet? Let's take a look at this thing. Can y'all see my screen? Yeah, it looks like you can. We got fires all over the place. I love it. I see some stuff that's likely. I see some stuff that might go uncaught. Let's go through and take a look at some of this. But first, what I like to do, before I even go in and look at specific risks, I like to look at the picture holistically as a whole and identify if there are any places where these icons are like concentrated, you know? And in particular, if there are risks that have several of the different amplifiers. So something that's catastrophic and likely and could go uncaught is the kind of thing that absolutely needs my attention, that needs my team's attention right away. Because that is a high priority risk, right? It has all of the amplifiers associated with it. Good example of that might be, you know, a vet puts something in wrong and it ends up corrupting information in the database in other rows in ways that goes uncaught. But we need that information to be able to treat the parrots. And if we can't do it without that information, then it's also catastrophic. That might be an example of a risk. And that's one of the reasons that form validation actually is built in to a lot of front-end products. Anytime that you're building a form with almost any technology, it'll have built-in affordances to help you with form validation. Part of the reason for that is if you're not doing any validation on your form, it's very easy for the wrong inputs to like accidentally mess up your system. Pretty bad. All right, so let's take a look at some of these things. I'm going to zoom in and see what risks you have identified. View, zoom, 100. I love this. It's like looking at a little city of terror. Okay. Poor security leads to data tampering. Yeah, that would be pretty catastrophic. I see a lot of likely over in this area. Mixed breed input incorrectly, invalid breed. Yeah, absolutely. You've identified a high likelihood. Mixed breed parrots are not that weird. They're not that weird. And we have to make sure that our data accounts for that. Somebody might bring in a parrot. They don't know the breed is missing, the breed is wrong. It's really important for us to be aware of the extremely large likelihood that the boundaries of our model are going to be wrong when they interface with reality, right? No data model survives first contact with the real world. All right, so let's look around for some other little groups. I see a little grouping right here. Look at all these detectives in the same spot. What's happening here? Incomplete medical history. Yeah, that might be likely to go uncaught. Because if the patient's owner isn't telling us anything, then we don't know. Then maybe something happened to the bird in the past. It's really important for us to know about. Incorrect input cases, yep. System crash, well, I think this one is actually for, oh yeah, nuanced diagnoses. An algorithm can't account for every possible scenario. Yep, this is absolutely something that we need to be aware of. This condition risk evaluator is effectively performing the role of a triage nurse, which is typically something that you have a highly trained professional doing, right? So we need to be really aware of what this system is allowed to do and what it's not allowed to do. At what point are we making sure that a trained veterinarian is taking over? Because there's going to be a point where that absolutely has to happen. All right, let's look at this other one. The threshold may not be reliable for all cases. Yep, absolutely, right? Maybe we have a bird in there that's just dramatic, gets worked up real easy, and that bird doesn't always need immediate attention, right? That might be a situation, right? That could potentially go uncaught. Delayed notifications, yeah, delayed notifications might go uncaught because we don't necessarily know. We don't know how long the bird has been in distress. So we might not know when we show up, like, hey, this bird has actually been in distress for a while and we weren't getting the notification. See if we could identify any more clusters. I see a little bit of catastrophic cluster here. Crashing, threshold might be broken, presumably potentially crashing. Oh, I moved that by accident. All right, and then we got a lot of likely up here again. Let's talk about these likelies. Condition risk evaluator depends on 3 services to proceed. Yeah, might have scaling issues. I don't know if these 2 dice are supposed to mean that this is super likely, but I choose to interpret it that way because the truth is that when you have something, like if this thing depends on all 3 services being operational, then, and it doesn't operate, if even just one of those services goes down, then we've got 3 potential points of failure here. That's a lot of points of failure. So we want to make sure that any one of those, that we do what we can to make our system robust against, like, if one of those things goes down, maybe there's something it can still do to operate. Maybe there's a backup system or something like that, right? So as a software engineer, what I could do is come in, let me zoom out again, and take a look at this chart and identify where I need to allocate my engineering resources first. Because I want to go to the points on this chart where these risk amplifiers are concentrated, right? Where those risks are going to mean, where reducing that risk is going to mean the most for the team, because these risks are, for whatever reason, bad, right? Now, we would talk more about that in detail in like a real lecture, but this is a sample lecture, so we will call it on that subject and say that this is a teaser. You can come here to get the rest. But now let's move in a little bit to what you do about this situation. So we've identified all these risks and we've prioritized them. We know what we want to do. And so then we have to figure out, how are we going to mitigate these risks, right? How do we bring the risk level down? Well, you've started to do a little bit of that work already by identifying what amplifies each of these risks. What makes each of these risks bad? We're not just going with a gut feeling anymore, right? We have this image that tells us what's catastrophic, what's likely, what might go uncaught. So now we can talk about how you might reduce the consequences, reduce the likelihood, increase the catchability on our risks, right? There are all kinds of things that we could do. I'm just going to give you some examples right now, but it's not an entire list. And we're not going to go into the implementation on these things, but I want to give you a flavor. So for reducing consequences, we can do things like fallbacks, right? We can have sensible defaults, or we can say, if the server goes down and the whole system is porked, then we need to make sure that we have backup servers, right? We could increase tolerances. So for example, maybe if a vet's phone might stop getting notifications if it runs out of battery, then we can put the device in low power mode if it goes below a certain amount of battery to make sure that it's going to last for the vet's whole shift. How about redundancy? Well, this is an example. Backup servers, for example. We could do a backup cell network if the cell network is down. A better example of a fallback might be if it's an unknown breed, then we have a general, like, sort of generic, large birds have these vital signs usually kind of system. That's not as specific as the breed API, but it's like a cached, very simple thing at the condition risk evaluator level, so that if the breed information API is not available, we have a fallback that kind of makes sense. So those are some of the ways we might reduce consequences, right? Now, maybe, what about those likely risks? What about those things we had all those dice icons on? Well, we can do a lot of things to reduce likelihood. We can use automated tests, so we can write code that makes sure that our other code is correct. And that's one of the things we'll talk about in the MPCS. We'll talk about quality assurance. So quality assurance is getting usually trained professionals to make sure that things are working properly. These are folks who know exactly how systems can break, and they'll try to exploit those systems in order to make sure that those things aren't going to happen. Or we could use regression checklists. So this is a list of features. It's probably the simplest of these three. It's a list of features, and every single time you deploy new software, you go down the list and make sure all of those things work. Sounds intuitive, sounds pretty simple. Checklists are one of the primary means by which airlines make sure that everything is good to go. Checklists are one of the primary means by which rocket launch is green-lighted to go. So that's reducing likelihood. So now let's talk about increasing catchability, right? So if something's likely to go uncaught, what can we do? Well, one thing we could do is use frequent and descriptive logging. Logging is when we have a big file that acts as sort of like a journal for our application. And every time somebody visits a certain page on our app, then it gets logged. Every time a crash happens on our app, it gets logged. Every time some data comes through our system, it gets logged. Frequent and descriptive logging means that when something breaks, we can go back through the logs and try to figure out what happened and why. Frequent and descriptive logging is really important for production software. Another thing we can do to increase catchability is penetration testing. So in particular, penetration testing is what you do to make sure that hackers are not going to be able to get into your system. And the way it works is that you have engineers who specifically try to hack your system. But instead of taking advantage of you when they hack your system, they give you a report of all of the ways that your system could be hacked and how you can go about closing those things up. Auditing is a little bit similar. Suppose that you have personal health information, personally identifying information, financial information. You're likely to be subject to auditing. And auditing is when somebody goes through and makes sure that you're handling that data correctly so something really bad doesn't happen when you push to production. Now, typically at this juncture, what we would do in the MPCS is that we would go into another group exercise. And this time I would have you go back through that diagram, this time with blue text instead of red, and mention how you might mitigate each of the risks you'd identified in the system. Starting, of course, with the riskiest ones where all of those little icons are clustered together. We're not going to do that today because I got to leave something to teach you for when you come here, right? And because that exercise is, I think, most productive after you have a couple of classes under your belt where you've learned some things about each of these different mitigation techniques. But now you can start to see where some of that information might be useful, how you would end up using some of that knowledge that you're getting in the MPCS when you're working on production software in industry. All right? So I'm going to leave it there for now, but I do want to leave you with this thought, which is that identifying risks and undertaking prevention and mitigation strategies is one of the things that's really key to engineering. And that's something that's true on any stack, in any language, in any year, for any hardware or any software. That skill remains important. Whether you become a Python programmer or an iOS engineer or an Android engineer, or you end up working on compilers, or you end up working on real space launch systems, having a skill set like this is going to serve you well on those teams, and it's going to serve you well on those projects. And that's the kind of thing that you could expect to get from a lecture here at the MPCS. And so we're hopeful that you will come and join us